If you see the working of this module, I will see if we have the VLC media player, probably it will work. Yeah, have a look at it. See, what is happening is one bit of the device is being picked up. Oh, I think I need to replay the video. I think it did not get copied. Anyway, let it be. So it picks up and then it will put it back into a homing position wherever it likes to put, and then yeah, I think there is a problem. I will try to bring it back later. The issue being that each of these wells we can maintain it at any temperature we like, and then we can have these what do you call thermoelectric modules built into it, or one place we can probably have the thing copied and whole thing to be kept in a place as we like. I will now move on to another important thing called heat pipes. In passing, if you remember, I had mentioned to you about a nice way of cooling things which are in a way relatively passive. The idea of passive is, in the case of Peltier, we need to supply huge amount of power to it. So, my own what you call empirical thing is that 3 to 4 times the amount of total energy is required to cool a given unit. This I think so many times even earlier I have explained to you, saying at one point this is a working fluid inside a normal what do you call pipe. Instantly the pipe can even be an insulator, it need not necessarily be made of copper, but the end where it is collecting the heat needs to be a conductor, other end which needs to be cooled needs to be another conductor. In between you have these wicks. So, working medium boils, condenses here. Now, read this. So, you will notice that when we talk about power electronics, we end up with very small rise in temperature with given wattage. Now, we will come back to the beginning of it and see what it is that they are talking about. Old heat pipes are basically vacuum sealed tubes. They keep high power electronics cooler than traditional heat sinks. So, if you go down, in its simplest, a heat pipe is a heat mover or spreader, takes heat from a source such as power conductors and moves it to a region where it is readily dissipated. Heat pipe moves this heat with minimum drop in temperature. A typical heat pipe is a sealed and evacuated tube that contains a porous wick structure and a very small amount of working fluid. Porous wick is a sintered powder metal that lines the internal circumference of a tube. The central core is left open to permit water flow. An evaporator, an adiabatic and a condenser. As heat enters and so on, you read it for yourself. So, yourself you can go to thermal things and see things that have been given here as it is. So, lot of analysis has been carried out. So, it is a matter of, I think, at your leisure you can read things. Test results: heat pipe assembly was tested compared to the CFD predicted. 6 heater blocks simulated the high power IGBTs, thermocouples mounted and so on. Acoustical noise is a thing. At these state conditions, the average measured block temperature was 76 degrees. This yields a thermal resistance value of the entire heat sink of 0.006 degrees centigrade per watt. So, this is the sort of things which we are talking about all the time. Somebody has made this what you call presentation. I suggest you can try to read about it. Typically, heat pipe work I have used. What is a heat pipe I showed you? What are they used for? I mean, it is there absolutely. This is a very interesting thing. Seen that the intentionally I wanted to show you in print. Effective thermal conductivities can range from 10 to 10,000 times the effective thermal conductivity of copper. So, figures do not lie, these are not statistics. So, they are not other type of lies also. So, we have here lot more. What are the 4 basic heat pipe transport limitations are: capillary limit, this is the maximum capillary pumping pressure of the wick structures transport the working fluid from the heat pipe condenser to the evaporator. Capillary pumping pressure must overcome the basic pressure drops within the heat pipe. vapor pressure drop, liquid pressure drop and gravitational body force pressure drop. So, orientation also seems to make a difference. Next comes to boiling limit. The boiling limit occurs when the maximum radial heat flux is exceeding resulting the rate of working fluid vaporization to exceed the rate at which liquid condensate is returning from the condenser section to the heat pipe. It is a little like your mud pots. There is a general, I do not know if it is a myth or what do you call, nice dream, a romantic dream, that if you take a porous pot and then put water into it, it becomes cool. There are people who claim, I find it as cold as a refrigerator. That is, if you have a good cooling system, I mean what do you call this, evaporative cooling versus a bad what do you call, normal refrigerator, probably they are about the same, but it never can beat a power in device, and the rate of diffusion of the liquid through the what do you call that material of the pot has to match with the evaporative capacity. If everything is matched, you get the cooling which we are talking about. So, it involves two things, dryness of the air outside and the amount of air that is flowing and so on. Same thing happens here, rate of working fluid evaporization and liquid condensate returning from the condenser section of the heat pipe. When the boiling limit is reached, liquid working is not available to absorb heat, the heat pipe goes into a dry out condition and will not operate. The whole thing becomes hot and it is not able to this thing what you call operate. Maximum flow rate of the working fluid travelling from the heat pipe evaporator condenser. When the heat flow exceeds the sonic velocity, choke flow is achieved and the heat pipe will not operate. And entrainment, when the shear force of the vapor flowing from the evaporator to the condenser or the heat pipes at the interface causes liquid droplets to be entrained and carried to the condenser, exceeding the entrainment, so on. In certain conditions it will not work. So, it is unlike putting a simple copper tube and expecting it to work. So, are they reliable? Of course, yes, they have no moving parts. Ideal for applications such as aerospace, where maintenance is not feasible. Main cause of heat pipe failures is gas generation in the heat pipe, can be completely avoided by proper cleaning and assembly procedures, and so on and so on. Are expensive? Yes, initially they are very expensive. To start with, as happily ignored the design cost and this thing, it is not simple to design those things. If cooling can be performed by simple conductive heat sinks, that is the best way to do it. In more demanding applications, overall cost of heat pipes is competitive with other alternatives. Initial cost is partially offset by improvements in system reliability and increased life of cooler running. Large quantities, the cost of heat pipes drops significantly and makes them the most economical solution to a cooling application. So, typically in that what do you call IGBT cooling and all that, and I have also shown you in the earlier picture a game console. Such places you have a margin and the reality is there, but then you remember in some of the game places even forced liquid cooling is used. And we come to important thing, can they work against gravity or it has to be horizontal. The pictures they have shown there is shown horizontal. In these applications, working fluid must be pumped against gravity back to the evaporator. This occurs through wick structures and pump working fluid through capillary pressure. Finer the pore radius of the wick structure, the higher against gravity, nanoscale. Not all types of heat transfer can operate against gravity. A thermosiphon is similar to a heat pipe, but has no wick structure and will only operated in gravity aided. So, depending on, it is natural. If the condensing section is on top and the heating section is on the bottom, obviously it can work. If it is upside down, it will work slightly differently. So, we have working fluids of helium and nitrogen for cryogenics, to liquid like sodium and potassium metals for high temperature heat dissipation. More common heat pipes use ammonia, water, acetone and methanol. You can make it yourself. If you go to YouTube, I will show you one or two pictures of those things. What we have is probably normal alcohol, that is what you call methyl alcohol, and this acetone is a common solvent. So, a mixture of all these things. So, we have all this stuff here. So, all these things I suggest we will get back if there is a way of coming back. So, we have so many things which are mentioned here. Let me show you a little more about a few other things. I could not retrieve the thing in time. So, these are all basics, and you will notice that these are all probably spin-offs of various what I call government sponsored or things here. So, this is basic working, and you see here we have beautiful assemblies here which have all these things. Now, myths, I think you should read it yourself. It is not liquid cooling. So, it does not need the type of pressure tight what do you call design, and it is generally being under a vacuum, and the moment any leakage comes, no liquid will ever come out and likely to short circuit your device as compared to water cooling or other things. Okay. The minuscule amount of liquid actually within the pipe would be fully saturated in the wick, so no fluid will drop out. Second myth, heat pipes are heavy. The moment you talk about piping, you probably confuse it with plumbing. Not necessary. What looks like a simple copper tube with two projections at both ends, the reality is it is not true. So, if we were to use a copper pipe which has the equivalent thermal conductivity and huge heat sinks, that will be much heavier than a heat pipe, because the basic place which we take away heat from, that will be small, and the working fluid, and that will be small. The last heat spreader will be about the same, because you need to spread heat to the ambient, and then the temperature, only thing is you have a little bit of control. You can make the heat sink run at a higher temperature. The more delta T with the ambient, that is heat sink surface temperature to the ambient, the better the heat transfer is. As I have explained to you earlier, a cold heat sink is not doing anything. It is just meant for decorative purposes. And another important thing is, there is a more open area of the device where a fan can be added to decrease the size and weight of your cooling solution. So, you take away the heat to a convenient point. Then very interesting thing here. So far things we have shown are, there is a long tube in which there is a warm and cold region, and hence it should be a long thing. Heat pipes have design flexibility, they can have more cost efficient solutions. Heat pipe being used with the heat source at the center and the evaporators at both the ends. You have seen that, no? The heat is being spread into two structures. So, we have here heat source which sends it to the various places and where the evaporation can take place. Heat pipes only spread heat in a straight line. If I want to spread heat along the whole base, I need a vapor chamber. And here it is given here saying heat pipes can be bent and used in a manner similar to vapor chamber with more structural integrity. Vapor chamber is what elsewhere it will come. It is a small thing which is mounted on top of a chip, so that the boiling and condensation can be taking place at about the time. So, we have here a heat pipe which looks a little like a vapor chamber. Next, it has to be very hot for heat pipes to work. That is another thing which is true in the case of actual simple convective heat sinks, but in the case of what you call heat pipes, we have a control of it. The temperature of the heat source does not need to reach the standard room temperature boiling point to cause the liquid to change. In fact, a few differences needed between hot end areas of a heat pipe to make it function. One of the advantages. Then heat pipes cannot be used in freezing conditions. How a heat pipe operates in environmental conditions dependent on materials and design. Heat pipes can be developed to function in extremely rugged conditions such as freezing environments also. Expensive? No, because he is the merchant who is selling it, and for a given application it is not necessarily to be that expensive. We have various options here to worry about or rather start making things as we like. Now, I thought I will take you to some links which I have saved. I hope I am able to retrieve it here. It has to connect to the what do you call our internet. So, one of our Professor Dasgupta and Dr. Somnath Ganguly of IIT Kharagpur, they have made this video, and some reason it does not seem to be loading fast enough. So, next round when I get a chance, I will post these links to you, and I am sure you will be able to retrieve these things and show them how well they work. So, at this point probably I will give a break, and we will try to get back and see how best we can. There is some problem with the there is some problem with the video. I am not able to show it. Eventually I will show it. So, thank you. After I download the videos, I will try to show you. So, thank you for a while now.